Welcome to the video. We are back with yet another exciting research paper implementation. This time, we'll be showcasing the work on the paper titled Explainable Automated Coding of Clinical Notes using Hierarchical Label-Wise Attention Networks and Label Embedding Initialization. Medical coding is a critical process that translates clinical notes into standardized codes for billing, research, and clinical analytics. The research paper at focus in this video introduces an innovative approach designed to do just that. So let us start with the problem statement. Manual diagnostic and procedural coding of clinical notes is a time-consuming and error-prone process. This method involves manually assigning standardized codes such as ICD-9 to discharge summaries and clinical records. The variability in coding practices among different healthcare professionals leads to inconsistencies and inefficiencies. Automating this process could improve both efficiency and accuracy. However, current models in automated medical coding often lack explainability and fail to capture complex correlations among medical codes. This can limit their reliability in real-world clinical settings and hinder their adoption. An effective and explainable automated medical coding system would significantly improve efficiency and consistency across the healthcare industry. The objective of this paper is to address these challenges by automating the medical coding process using advanced machine learning techniques. The authors addresses two key limitations in current models: the lack of explainability and the failure to capture complex correlations among medical codes. By integrating hierarchical attention networks and hierarchical attention bidirectional gated recurrent units, this paper introduces a model that highlights important words and sentences while providing detailed explanations for each label. Now we will have a brief introduction to the data set that was used for this research. Mimic3 is a large, freely available database comprising de-identified health-related data associated with over 40,000 patients who stayed in critical care units of the Beth Israel Deaconess Medical Center between 2011 and 2012. The database includes information such as demographics, vital sign measurements made at the bedside, laboratory test results, procedures, medications, caregiver notes, imaging reports, and mortality. The Mimic3 database was populated with the data that had been acquired during routine hospital care, so there was no associated burden or caregivers and no interference with their workflow. The data consists of over 50,000 annotated discharge summaries, which is approximately 1.5 GB in size. The data is available in text format, which is already pre-processed and labeled with ICD-9 codes. Now that we are familiar with the data set, we'll look at the steps that were taken to implement this research paper. So the first step in the implementation is data pre-processing. First, we clean the text data by removing unnecessary punctuation and numeric only tokens, but we made sure to retain relevant numeric information like 250 milligrams that could be important for medical coding. Next, we normalize the text by converting all characters to lowercase, ensuring consistency across the data set. We also organized the labels in sequence, which was crucial for effective training. We then generated a vocabulary file from the discharge summaries, which served as a foundation for word embedding. To enhance the model's understanding, we pre-trained the word embeddings using these summaries, providing the model with richer input data. For label embedding, we leveraged the correlations between labels found in the training data to initialize the final layer of the model. This step gave the model a head start by incorporating existing relationships between medical codes. Finally, we manually split sentences before feeding them into the tokenizer, optimizing the input for better processing within the model. These pre-processing steps were essential in setting the stage for accurate and reliable automated medical coding. The next step is model implementation itself. In this section, we'll be introducing the key models implemented in our approach for automated medical coding. First, we have hierarchical attention networks. This model uses attention mechanism to highlight the most important words and sentences in a document, making it easier to understand which parts of the text contribute most to the final prediction. Next is the hierarchical attention bidirectional gated recurrent units. This model builds on Han by offering sentence level explanations for each label. But it still falls short in pinpointing the specific words that lead to each decision. Finally, we implemented the hierarchical label-wise attention network. This novel model combines word level and sentence level attention mechanisms for each label, offering richer explainability by identifying not just important sentences but also the key words that influence the prediction of each medical code. Now that we have some inkling about the models, we move to the next step, which is evaluation. In order to assess the performance of the models, we made use of two metrics, which are micro F1 score and micro ROC AUC score. The micro F1 score measures the harmonic mean of precision and recall, providing a balanced view of model performance across all classes, whereas micro ROC AUC score evaluates the area under the receiver operating characteristics curve, indicating the model's ability to distinguish between classes. Now that we have developed an understanding of the pipeline that went in the implementation of this paper, we are ready to move to the last and final section where we are going to discuss our results. Our evaluation of different models showed varying levels of performance. You can see the results from the paper and the results from our implementations in these tables. Our model results are close to the paper's benchmarks, showing that the HLAN plus LE approach is particularly effective, though there is room for further optimization to match the reported performance levels. If you are inspired by this demonstration and would like to leverage our expertise for your own research or projects, don't hesitate to reach out to Codersarts. You can contact us via our email ID, which is contact@codersarts.com, or you can also get in touch with us via our website, which is www.codersarts.com. Whether you need help with data replication, machine learning models, or any other technical challenge, our team is here to support you. Like, share, and subscribe for more insights into how technology can transform healthcare. Thank you for watching the video.